Today's video is going to be about CUDA, which is a framework that NVIDIA developed to let you program their GPUs. So how does CUDA relate to AI? Before we get into CUDA, I want to make something clear. Most people building AI applications do not need to write CUDA code. I copied this diagram from the ebook called Inference Engineering. So there's an ebook called Inference Engineering, and I copied this diagram from it. In here, you can see that there are frameworks such as PyTorch and TensorFlow at this layer. And these frameworks dispatch the actual computation to the optimized GPU kernels underneath them. So on non-NVIDIA hardware, they can use a different backend instead, other than CUDA. So an application developer normally would describe what the computation he wants is, and the framework itself, for example, PyTorch or TensorFlow, would handle how that computation runs on the GPU. So if your goal is to build an AI project, serve an existing model, fine-tune one, or experiment with open models, do not start by writing GPU kernels. Start with the free online book, Inference Engineering. It gives you a practical map of the full inference stack, for example, the model, serving framework, performance techniques, hardware, and infrastructure. Then go on huggingface.com. I actually don't remember the website exact URL, but it's Hugging Face. It's one of the easiest places to learn how to find models, load them, run them, fine-tune them, and build actual applications without touching CUDA. So who's this video actually for? It's for people who reach the point where the existing abstractions are not enough. That could be like a machine learning systems engineer fusing several applications into a single kernel to reduce memory traffic and inference latency. Or it might be a researcher implementing a new attention mechanism. It could be a library engineer who works at a company and he's trying to build a new backend to integrate with PyTorch or TensorFlow. It might be someone doing numerical computation where he needs to do parallel work, so the CPU is not a good tool. He needs to use the GPU instead. So in other words, this video is about the layer underneath the normal application AI development, which you probably will be doing. So if you don't need to write custom GPU code and kernels, you're better off just learning PyTorch and TensorFlow and going on Hugging Face and just use existing inference engines. It'll be much faster for you than going through this video and learning CUDA. But once you do need control over thousands of GPU threads, CUDA is what you need to understand. So that's what this video is for. All right, so here we have CUDA, threads, blocks, grids, cooperative groups, and memory. Okay, so CUDA can look like a pile of special syntax, but most of it comes back to three simple questions. The first question is, which thread owns this piece of work? The second question is, which threads need to cooperate with each other? The third question is, where should the data live? The picture on the slide is basically a summary of the whole video in compact form. A thread is one worker. A block is a team of workers. A grid is the full job created by one kernel launch. The memory on the right, you can see it follows the same idea of scope. Some data belongs to one thread, some to one block, and some is visible across the device. We'll unpack that model one layer at a time. Okay, the next slide here, you can see one kernel launch creates one grid. Okay, so this whole picture is just one grid, and it's broken up into blocks, and each block has threads. So this is one grid, this picture that you see, the whole thing is just one grid. Okay, every thread runs the same exact kernel function. What makes a thread unique is the built-in position. So keep that in mind. What makes a thread unique is the position in the block and in the grid. Its thread index inside the blocks and the block index inside the grid. The block is an important cooperation boundary. Threads in the same block can share the data through shared memory, and they can wait for one another at a block barrier. Different blocks are normally independent. CUDA doesn't promise which block runs first. that's really important to keep in mind, that you can't make one block run before the other. It's not a flaw, it's just what lets the same program run at scale across the GPU with a different number of processing units. Okay, so here we can just see a example. Notice the global keyword. That's really important at the top left, the global keyword. This keyword marks that this is a kernel. What's a kernel? A function launched by CPU code. So the CPU code launches this function, and it's executed by GPU threads. Every thread reaches the same line that calculates I. So you can see block index.x tells which block we are in. So this tells you which block we're in. And block dimension.x tells how many threads there are in each block. So you put those together, so you get a unique index across the entire grid now, which is I. I is the unique index of this thread across the entire grid. And then you have an if statement, which is just a safety check, because you're going to have at the end a bunch of threads in the very last blocks that could be outside of the data. And you usually just have to round the grid size up so there's enough threads to cover the input. This means the last block, like I said, probably contains a few extra threads. And those threads must not read past the end of the arrays, or else you're just reading past the end of your data, which is not good. At the bottom, you can see this is where the actual, kernel gets launched. This is where the kernel gets launched here at the bottom. So this is NVIDIA syntax. You can see the three, I think it's called triple chevron notation. So this launches 256 threads per block. And at the bottom, it uses ceiling division. Okay. We can move on to the next slide here. Okay, global indexing formula. So let's talk about this. This gives you the thread, like I is per thread, and this is going to be unique within the entire grid. So you launch the kernel and you get a grid and like a lot of threads. And this is how you get the unique index of that thread or that copy of the kernel within the grid. So CUDA starts at index 0. In this picture, you can see the highlighted thread is thread 5 inside block 4. And every block contains 8 threads in this case. 4 complete blocks come before this one. Okay, I'm talking about the highlighted yellow one right now. So 4 complete blocks come before this one. So 4 times 8 is 32. And then you move 5 positions into the current block. That gives index 37. You see how I would be 37 in this case. So once a thread has that number, it can be used as an element index in a linear array to map to the initial data that you provide to the kernel. Okay, so CUDA blocks and grids can also have 2 or 3 dimensions. That doesn't create a different kind of thread. It's the same kind of thread. It just launches the thread. It just gives the launch shape that matches actually the problem. So it just changes the launch shape, but the underlying thing that happens is the exact same. So for an image or a matrix, the x coordinates would naturally choose a column, and the y coordinates choose a row. The column formula is one-dimensional applied in x, you can see right there. The row formula is the same thing applied in y. The data is still usually stored as a flat array. Keep that in mind. Once we have a row and a column, we flatten them with row times width plus column. Oh yeah, you can see it right there. Row times width plus column. So a 16 by 16 block contains 256 threads right there. Because you're just multiplying the dimensions like a square. Okay. So here we have a code example of matrix shaped work. Okay, so the matrix code right here is the same one thread per element idea with 2 coordinates. Okay, so there's column and row. So it's one thread per element, but there's 2 dimensions now. So each thread calculates a column and row, The bounce check protects them, like we saw already linearly, but this is just two-dimensional bounce check. So the launch shape mirrors the data shape while the underlying memory stays linear. So there's another concept here called cooperative groups. This was introduced, I think, in like CUDA version maybe 9, something like that, 9.0 if I remember correctly. So inside a block, the hardware organizes threads into warps of 22. Cooperative groups give us C++ objects that name the threads that are supposed to work together. Okay. All right. In this diagram, you can see there's one block that becomes two tiles. Each tile has its own rank from 0 through 31. So there's 32 total, so it's just 0 through 31. And the yellow thread would be rank 0 right there. Like you can see it's there. The big benefit is clarity. A helper function can receive a group and say in code exactly which thread participate in its shuffle, barrier, and collective operation. It's safer than hiding the assumption like the whole block must call this function in a comment. So it just makes it more explicit. You can see a like actual code example here where, so at the top, obviously we're including cooperative groups.h. If you look at group sum right here, and then offset, and then shuffle right here, group shuffle down. Okay, this helper adds the value one by one tile. So this helper adds the value by one tile. The offset begins at half the group size. For a 32 thread tile, that means 16. Each thread pulls a value from a thread 16 ranks to the right and adds it to its own value. Then the distance shrinks to like 8, 4, 2, 1. So it just divides by half each time. It's just right there. You can see 8, 4, 2, 1. And it forms a reduction tree. And every step just combines the partial sums until rank 0 holds the tile's total. So shuffle down right there just moves the values directly between threads in the group. So this specific reduction doesn't need shared memory, which we're going to talk about, shared memory. The memory is really important, actually. And back in the kernel, the block is partitioned into 32 thread tiles. So each thread loads one input value. The tile reduces the value, and only tile rank 0 writes the result. At the end, you can see this is where the result gets written. So tile rank 0, that's like where you write the result after first computing it. So this produces one sum per tile, not one sum for the whole array. So it's just one sum per tile, like I said. And that launches should use a block size that's obviously a multiple of 32. So every tile is complete because you're dividing like 32 warp, and then you divide by 2 each time. And then there's like there's a way to basically stop the block boundary here. So you have grid-wide synchronizations possible, but it's a special case. So if you see this underscore grid, it just creates a group that represents the whole grid. So every thread first doubles its element. You can see every thread just doubles its element. And then you have grid.sync right here. So it's just grid.sync like makes the entire grid wait before the thread 0 reads the value produced in the first phase. Without this, the thread 0 could read the final element before the thread responsible for it had finished writing. So that would be a problem. And the catch here is the launch. The kernel has to be a cooperative API launch. Like you can see the comment in line 11. The device has to support it, and the grid has to fit into the device's cooperative residency limits. That's why grid.sync is not just a casual replacement for like double under sync threads. So in some algorithms, like you can end one kernel and launch the next in a cleaner grid-wide phase boundary. So here you could see memory hierarchy by scope. This is really important. So like the cleanest way to understand CUDA memory is by scope, not by memorizing like a rigid fastest to slowest list like you do with the CPU where you have like L1 cache, L2 cache, L3 cache. You don't do it like that in GPU memory. So registers, let's start here. We have registers. They're private to one thread, and the compiler usually places scalar values there. It's similar to a CPU register, so it's not that like hard to understand really. Space is limited. That's usually the case with the registers. Then you have shared memory. It's like a scratch pad for a block. So each block can share. Oh, it says that right here, block shared. Yeah, so each block can share the so one block runs on one streaming multiprocessor. You probably don't know what that is, but it's like a thing on the GPU. It's called a streaming multiprocessor. That's where shared memory is. So the whole block runs on the same streaming multiprocessor. So you basically just have a scratch. So shared memory, it's really important to remember that like the block can all access it. And threads in the block exchange, like they use it to exchange data. And yeah, so threads just use it to exchange data. Global memory is the large, right here, it's the large allocation for all the blocks. It's used for normal input and output allocation. It's accessible across the blocks, and an allocation remains until the program frees it. So what else do we have? Constant and texture. These are specialized. You probably don't need to worry about these, but constant is used for small read-only values that are shared by many threads. Constant you do use actually, but texture, it's it's useful when caching or addressing behavior matches the data addressing. But yeah, it's specialized. So and then L1 and L2 are hardware managed. You don't really declare L1 or L2, but I forget which one. I think shared memory and L1 are shared. I can look that up. But something and L1 share the same memory. I believe it's shared memory. And L1 share the same memory space, so the more you allocate to shared memory, it consumes more L1, and then you have a smaller L1 space when you use more shared memory. Because I think L1's on the streaming multiprocessor, and then shared is also on the streaming multiprocessor. So if you allocate more to shared memory, you use more. And then you can also statically or dynamically allocate shared memory, but maybe that's not important. Right here, that's a static. You can see actually that's a static allocation. Like I said, line 4 is a line 5 is a static allocation of shared memory. So here you can see the under where the like double underscore constant. So I'm going to talk about the different memory types here. So you have double underscore constant at the top, and this is device code reads it, and the host code just initializes it before the kernel runs. And then you have input and output pointers. They just refer to global memory, and every thread can calculate an address through those pointers. And then you have extern double this thing right here. This is the NVIDIA compiler understands these things like global, constant, and shared. And extern shared right here is just dynamic shared memory. I think I said it was static, but it's actually dynamic now that I'm looking at it. And the host chooses a size when launching the kernel, and every block receives its own separate shared allocation. So dynamic versus static here means just that when the kernel itself is compiled, if it's static, then the memory is fixed when at the kernel compilation point. But dynamic means that when you launch the kernel, you can actually like specify whatever size you want it to be. So that's what the word static and dynamic means in this case of shared memory. And then you have a scalar right there named value, and it's just a normal candidate for a register. Each thread places its value in the shared tile, and the block barrier makes those writes visible before the block continues. And then you have the scratch array, which is private one thread. because it's a larger array with dynamic indexing, so the compiler may place it in local memory. The source code alone doesn't prove that to you. Like, you can't just get that from the source, but the compiler resource output is the only way that you would like check that. And just one last note that this is a scope demonstration, not an optimization recipe. So like if you copy a value into shared memory and read it only once, it usually buys nothing for you. Like, you don't get anything from that. So shared memory earns its cost when threads are exchanging data between each other or reusing data that's common to them. So yeah, that's it. And then here we have an example of shared memory. Okay, I see. So this is just a shared memory pattern worth remembering. So first, neighboring threads load the chunk of global memory, and then they place that chunk into the block's shared memory. Then the block waits until the shared tile is ready. After that, the threads can reuse or exchange those values without repeatedly fetching the same data from global memory. The pattern shows matrix tiles, stencil, convolution, histograms, reductions. You see this pattern in all of those things. And shared memory isn't magic. It helps when an algorithm has real reuse or communication inside a block, but it's also finite. So using more shared memory per block reduces how many blocks fit on the GPU at once. So here is a code example. Okay, so here every block produces one subtotal. So every block is just producing a single subtotal. And each thread loads the input value into shared memory, and a thread beyond the end of the input loads 0. So every shared slot has a valid value, you see? The first barrier matters because no thread, this is what I mean by barrier, like line 13. The first barrier matters because no thread should start reading a neighbor's slot until every thread has finished loading. And then you have a reduction that halves the active range of every round. So in the first round, the lower half adds the upper half. In the next round, half of those partial sums are combined again. This process just continues until the shared slot contains 0. Notice that the barrier is outside the if statement, right here on line 21. Some threads perform an addition and do not, and some don't. So, like, okay, some threads, like I said, perform an addition and some don't. But every thread in the block has to reach this barrier. So putting the barrier on a path that only some threads are going to take is going to deadlock the block. Why? Because it's just how single instruction multi-thread works. So you can look up single instruction multi-thread, but that's just how that works. And finally, you just have a thread 0 writing back the result of the block. So this example just launches a power of 2 block. And then here we have global memory. You have two different types of access, coalesced and strided. You can look at the picture to understand what that really means. Like on the left, you have neighboring threads, touch neighboring addresses. So that's called coalesced, when like you have thread 0, thread 1, thread 2. And then on the right, you have threads jumping through memory with a stride. This might end up with more transactions because the requested addresses are spread out. So there's a simple rule of thumb, is that when algorithm allows it, map consecutive thread indices to consecutive elements in the data. The vector add example does that naturally, and the matrix example does it in each row. So here's just a note, like the complete CUDA mental model. So I'm just going to go over the whole thing quickly. It's a kernel launch creates a grid, and a grid contains blocks, and a block contains threads, and the hardware schedules those threads in 32 thread warps. So the thread and block indices tell each thread where the work that it owns is, and threads cooperate inside a block to create shared memory and block scope synchronization. So cooperative groups can make that scope more precise by naming a tile, a block, or in some cases, a larger group. And this memory by scope is really important. I'll show you where you can memorize this in a second. So here, this is a technical reference. Let me see here if I can. This is a really good technical reference, I would say. Read this next if you want to read something next. This is definitely what you want to read. You go here and you read this, for example. This is really good. Tells you all about the memory types. Basically the things I talked about, yeah. So this is a good place to go next, I would say. Yeah, thank you.